Hi, I'm Merce Marti. I work for BigML, and before starting my presentation, I just wanted to share with you a big hug to those who are suffering from COVID-19 or are in lockdown, such as myself in Girona. And I hope that you receive my best wishes for you and your family. And the only message that I want to convey is please stay home and keep safe. You are the lucky ones, such as me, and we have internet access, so we can start doing ML right now. So let's start doing machine learning. And today my first conference will be how to build our first BigML model. In BigML, it's easy to build these models, as you will check today. But the first question that arises is, do I really need a model? Well, I would tell that probably yes, but it's not only me saying that. Also, Casey Kozyrkov, which is the chief decision officer at Google, shared this nice drawing showing the different profiles of people, maybe basically three groups. The first one is people that is curious about their data but has to take no decisions on it. Maybe they could just do data analytics. Those that make few decisions based on their data maybe would be happy just doing statistics. But once your business or your investigations have lots of decisions to make, and there's lots of potentially related variables to that decisions, to that outcomes, and they can share uncertain correlations with the outcome, then you're bound to use machine learning. Machine learning can help you greatly. So once we see that maybe we're interested in building models, you could ask yourselves, but how does a model help me? I mean, what will a model do for me? We've seen examples, and we have current examples of what a model does. The thing is that models are just behind the scenes, mostly in big companies. And all of you have made an acquaintance with that previously. When you read your mail, for instance, you receive a new email, and then as the data arrives, a model that is behind the scenes reads it and labels it, and it tells us, well, I think that based on the contents, this email might be a spam, and I'm just 68.67% sure about what I'm saying. And because of that, this mail goes into a spam folder, right, instead of our inbox. Also, if you do a bank transaction, then the profile of this transaction, the behavior, can just lead us to an anomaly score. I mean, there's some model behind scenes that reads the properties of this transaction, checks against the rest of transactions, and says whether this transaction is normal or not. And it gives us a score again, 69, 80 in the example. And based on that, we decide, we take action. So models here are labeling machines, right? Are something that help us to label the new cases based on our previous experience. And today, to do our first BigML model, we'll try a challenge which was published in Kaggle, and it's called Give Me Some Credit. And in fact, the question that we tried to predict was whether somebody will experience financial distress in the next 2 years. You can check this URL. There's data there for training and for test. And the idea is that what we want is to minimize the risk, of course, of someone not returning a loan by predicting the defaults for these loans. And the first steps in order to do that is just defining the question. And here's my small homage to the people in Monty Python, but this is a simple question, right? A silly question, but usually when you try to do machine learning, you must take into account the detail. You must be very careful about stating clearly all the details of your questions. For instance, a question not as simple as the previous one is, where do I consider that the customer is in default? And maybe in your organization, you can consider that when the customer misses some payments. Or maybe you want to consider that if the customer pays late. And finally, it comes to deciding what is the maximum delinquency that you would allow in your organization so that you label a customer as in default, right? So finally, you have to reflect on the question that you want to solve, the real solution to your problem. In this case that we're going to do today, it's easier because the contest already gave us a goal and told us that we wanted to predict who will be 90 days past due or worse, and we would only act on these people, right? Not on the rest of people that pay their loans. So now, what's the first thing that you have to decide? Well, the first decision is how to do that. And well, from our point of view, you can use the best platform built ever for machine learning, which is BigML. So I'll give you just some minutes so that you can sign in, the ones that you don't have a user profile in BigML. You see at the bottom of the slide, there's the URL where you can fill in your information. It's in bigml.com/account/register. And you see that if you fill in your information, like the full name, the email, and the username and password that you want, and use the promotional code MLSEV, then you will be granted a 1 month free boosted subscription, which means that you can use up to 1 GB of data and in 4 parallel tasks for all the new users that register with that promotional code. And while you're registering, then I'll explain to you what does the data contain, what does the file that Kaggle published contain. And in fact, the data dictionary is the first information that I need to give. I mean, when you share data with someone, with a colleague, it's not only about the pure numbers or texts that you're going to share, but also about the meaning of these numbers, right, and this text. So talking about the structure, the data dictionary that we're now going to work with has some variables. The most relevant one is the one that we would like to predict. Remember that we will provide some examples where we know really what happened, and we would like the model to build some kind of mechanism, such as we could just give new aspiring customers for a loan, and the model would tell us whether we should be expecting them to return these loans, right? So we see that the first variable that it's in boldface is seriously delinquency in 2 years. So there's a variable which tells us which customers were experiencing this 90-day past due delinquency or worse. And the contents of this variable, of course, will be something like a yes or no, something like true or false, 2 different types. And what we would like to do then for a new customer is classify them in one of these buckets, yes or no. Will he just pay his loan or not? The rest of properties or variables that we have, the fields that we'll provide in the data set, are fields related to the currency and the age and the profile of the customer that is asking for the loan, right? Whether they used unsecured lines, whether they were at 30 to 59 days past due the date, the age of the borrower, the debt ratio, so on and so forth. And that's the description of the information that we're going to provide. But the information itself will be, of course, a kind of table that will have many rows, 1 row per each customer or per each loan that has been asked, really, and 1 column per each property that we can provide the model with. So the idea is that we provide always the column where we provide the example of what happened with that loan, so the serious delinquency in 2 years column that you see first. And then the rest of columns are properties that might or might not be related to the fact that someone is delinquent in 2 years, right? So we provide the data and the model will choose whether one or another attribute, one or another property is related to this serious delinquency. But it's nothing out of that. I mean, it's a collection of rows with examples and a collection of columns with properties about these examples that might be related to the important property, which is the thing that we want to predict. That is in our naming is the objective field, the thing that you want to predict, and is in this case the first field, which is called serious delinquency in 2 years. That's the kind of structure that our data, our file has. And what we would like is to use BigML to solve that problem. So we'll do the first step, which is uploading this data to BigML. And first, what we need to do is, of course, finding this data in our local file system. In this case, I have the data. You can download it from Kaggle. I have it here in my local file system. I have already logged in the BigML platform. When you log in the platform, you'll see a menu similar to this one where sources is highlighted. And the only thing that you'll see differently if you're first-time users is that here you will see some files, some sources that have been previously created for you to play with. In this case, I've created an environment which is especially meant for this conference, and it's clean, has nothing in it, so that I can drop my data here. And that's what I'll do. I'll just drag and drop my data on the platform, and this will create for me a source. And what does a source mean? Well, you remember that we said that the first thing that we needed was the description of the structure of the data that we're providing, right? Then the source encapsulates that. It's how to interpret your data. The source is reading the first lines in your CSV file, and then the CSV file that I just uploaded, and it's trying to infer from it which files are there stored, which types do these files have, these fields have, sorry, and also, for instance, things like the locale, so the language in which this data is provided. And you know that this might be important because in English, for instance, the decimal separator is a dot, and in Spanish, to put another example, is a comma. So in order to interpret correctly your numeric data, we must make sure that we're using the correct decimal separator. Also, you need to know if your data has some text or some items that indicate that you don't have information about one of the instances. So if you don't have the information about the age of one customer, or you don't have the information about their debt ratio, then there will be some kind of text in your field, or an absence of text. And that's the missing tokens, the things that just point out that you don't have the information that should be there in that field. Also, if you had text or items, we should be telling BigML how to parse that. How can you parse the words? Even if it's inferred automatically, you can want to change that. So that's the kind of information that the source will store. And now we'll see what the source has made for us by default without our intervention, right? We just dropped in the CSV, which, as you know, is a collection of text or numbers separated by commas, nothing else. And from the first rows, BigML has inferred that the first row was different from the rest, so probably it contained the name of the fields. And it has created a naming here that tell you which are the fields that are in your file. After that, you can see that a type has been assigned to each of the fields. And this type has been inferred from the first instances in your dataset. You see here as columns the first instance, the first row of content really in your file, the second row, the third row, and as you can see, the first field, which is the ID, the identifier for each of the rows, has been interpreted as a number because they seem to be numeric values here. And the second one, which is exactly the thing that we'll be willing to predict, the serious delinquency in 2 years, has been interpreted as something categorical, because in the first rows, BigML has found that only 2 values were provided, 1 or 0, being 1 the value assigned to those loans that were not paid, that had serious delinquency in 2 years, and 0, the value that has been assigned to these loans which did not have serious delinquency in 2 years, right? And the rest of the fields, as you can see here, have also been interpreted as being numeric fields because of their content in the first instances, I repeat. So if I had made a mistake or I want to change this interpretation of the fields, you can here configure any of these characteristics so that you can change the type of the field to be sure that the model interprets correctly the information that you are providing. But as this inference has been correct so far, let's go to the next step. It's not enough to only have the structure of the information that you're providing. Of course, you need to inspect all the information that you provided in your file, and that's what the dataset does. Here you can see when you're in a source, you have a menu where there's a cloud with a thunder, and that's the actions menu. That's the one click, the thing that you can do just by clicking, right? And the first one of them is creating a dataset. The dataset is just inspecting the entire contents of the file that you uploaded, and is trying to build from it summaries. It's trying to summarize the information it contains per field. So what will we get from a dataset? The dataset will tell us how is data distributed along each of the fields. So we'll have information about how many rows were in the dataset, in the file that you just uploaded, whether there were some missings or not in each of the fields, whether we could find some errors, like, for instance, a datetime field that contained just characters or bad formatted data, and also the distribution of the values that you have in each of the fields that will be depicted for you in this case in histograms, as we'll see. And the basic number of statistics, mostly for the numeric fields, so that you can know the ranges of the values that you've provided in your file. And well, you can see that is happening here in BigML. Now, for the time being, it's analyzing the dataset, so the histograms are not yet complete, but you can start seeing things. You see that we have 150,000 instances in this dataset. It's a dataset with 7 megabytes. And we also have one of the fields which has 29,731 cases where the information is missing there. So it has already found out that there's some incomplete information in some of the fields. And also here, another one, number of dependents, which has 3,924 instances where the information is not there, right? There's no error so far in this file. And as you can see, the numeric fields like the age range from the minimal to the maximum values. Here you can see the statistics, the basic statistics for this field. As you can see here, there's a minimum of 0, probably because some of the rows did not contain the age information, and instead of that, they put a 0 there. But there's a mean of 52 years in this dataset, so the mean age of the people that are granted a loan is probably around this age. And also a maximum of 109, and good for them because we all hope to get there someday. And the idea is also that you have this kind of diagram, the histogram, which tells you how many instances are in each of these bins of these ranges, small ranges of the values in the field, right? Finally, in this case, there's this important field that we want to predict in this example that we're doing today, which is the serious delinquency in 2 years, that we said already that is a categorical, because there are some instances which did not have a delinquency. So instances where people paid their loans, these are the majority of them, thankfully, and they are 139,974 instances where the loans were paid currently. And then there's 10,026 instances only where there were some problems and people there were a serious delinquent in 2 years, right? These are the ones that we need to predict. So these are the ones that are important for us in this case. As we will be just working with this example and with this field and creating all the models just to create this field, to predict this field, sorry, I like to just provide the data set with an indication of that this field is the important one for us, right? Otherwise, all the models that we would create from this data set would expect the thing that we want to predict to be the last thing in the data set. But that is, as this is not the case, let me configure this data set and tell that the field that is important for me, the field that I would like to predict, if any, by default will be the serious delinquency in 2 years field. And that's our objective field here. The one that you see with a target next to it is the field that we would like to predict from now on using this dataset. We could do that also in the model configuration, and you will see it further on in the presentation. But let me do it here because we'll do it once and again. So once I have that, also let me tell you something about this mark here. You see that there's a red mark next to the ID field, and this happens because an ID is just a number which is randomly assigned to every row just by administrative purposes. But as each one is different, then there's nothing that this number can add when you try to learn from your data, because it has no relation whatsoever with the thing that you're going to predict. It happens that the same happens if you have a field where there's a single value always and it's a constant field. It will not help at all to the model to just separate or give us rules as to what can be related to the objective field, to the thing that we want to predict. So these kind of fields that are either unique identifiers or constant fields, they are marked with this non-preferred mark and will not be used once we try to build a model from this data set by default. If you want to use them, you of course can. There's this pencil here that would help you edit that and change this property, right? But by default, they are just left out, and the models that will be built on this data set will not use them. So let's go to the next step. And now the next step is starting making some machine learning. So far, we've only just seen statistics, right? We've seen which is information I have in my file, how does these values distribute all over the ranges of values that we have. But now let's build a model. So what kind of model would we build? Oh, this is a kind of classification problem, right? We have two categories, the people that pay their loans and people that don't pay their loans. And we want to classify our next customer into these categories. So when you have this kind of problem and you have a data set where there's some example of what happened in the past, you can use supervised learning. And if I go again in the data set to the menu with the actions available for me to work with, you'll see that we have some different models available that can deal with supervised learning, right? A model, an ensemble, linear regression, so on and so forth. In this case, I will use the model because it's the decision tree model, and it's the simplest, but also the more informative model that you can build from your data set. And in this case, just by clicking here, the data is analyzed, and the algorithm tries to find out which are the patterns that tell you when someone will pay their loan or not. What kind of insights will this model extract from my data? Well, hopefully, we would like to have some patterns. some kind of rules that tells us when this happens, then the customer will not pay, or when this happens, then the customer will pay. Also, we would like to know about which are the properties that really are related to the fact that someone pays or not. And that would mean having an idea about the importance of each of the fields that we provided in our file. And other things also, prediction and so on. But let me go back to the screen and see that BigML has already built a model for me, and the result will be placed here whenever I ask for a prediction. But let me interpret this visualization that I'm showing to you right now. This is a decision tree, and the name is related to the fact that this is like a representation of a tree just turned upside down, right? We could say that the root is here. You start having all the data that you provided, all the examples that were used for the training here at the top. And there's the 150,000 instances that we saw that our dataset contained. And you see here also the distribution, right? You saw in the previous screen that we had 139,974 that were representing loans that were paid, and some loans, 10,026, that were not paid. What does the model tells us here at the root without asking about anything? I don't know anything about the new customer that comes to me. Well, the model tells us that statistically, mostly the loans are paid. So probably if you know nothing about your new customer, the prediction is that he will pay his loans, or she will pay her loans. And the confidence for that prediction, given the difference between the cases where the loan is paid and the cases where the loan is not paid, it's 93.90%, so a high confidence, right? And what happens if I start making questions? Well, the first thing that you see here on the right is that a question appears. So what's the number of times that the customer has been 90 days late? That's the first question that the model does in this node, where you have all the information. And depending on the response, you will go through one branch for the people that has not been ever 90 days late, or through another branch for the people that has been 90 days late. And as you see, the difference here is it's quite big, right? I mean, here the people that has never been 90 days late, it's hugely, immensely just going into paying their loans, right? But here, as you see, there's still a lot of people that would pay their loans, even if they have been 90 days late, but there's more people that will not pay her loans in this group. So the groups are more balanced, right? If I go on making new questions, like here or here, each node will split again depending on the answer to the question that I'm posing. Here you can see that on the right, the questions that I'm posing and the answers are being depicted. And going down and making more questions, I would finally reach a node where I would have no more questions to ask, because you cannot, you have no more information, no more properties that can help you separate this kind of instances, this kind of customers. And here, mostly following that path, I would find a group of customers that have a similar pattern and finally pay their loans, right? But what if I'm interested, as I am, in the people that don't pay their loans, okay? I could filter out this tree and see only the nodes that end up in people that are not paying their loans. So if I do the same, again, I would go here or here or here and ask many questions till I find out a case where mostly people don't pay their loans. And that would mean one of the patterns that people that don't pay their loans follow, right? I mean, here on the right, you see which are the questions that have been answered to create this pattern, this rule. And you see that, for instance, here, people that have been more than once 90 days late, and more than once, more than 0 times, so sometimes 30 to 59 days, and are over 22 years of age, and also have revolving utilization of unsecured lines. That's the last, sorry, lines of credit. That was the last question. Then here, then they finally end up not paying their loans, right? This is one of the many patterns that you see here represented that can lead to not paying their loans. So here we find out part of the information that we wanted, right? We wanted a way of telling which are the things, the rules, the patterns that follow the people that don't pay their loans. And also we have a way of knowing whether, given a new customer answering all these questions, we can classify him or her into one of these groups, into the groups of people that don't pay their loans. So we can predict, based on our previous data, what will the new customer do? And that was our end so far. You can also see here that there's a confidence associated to that prediction. What does that confidence mean? The confidence is giving you an idea of how sure is the model based on the data that you provided to train it, and only on that, of what is telling us. Here you can see that not everybody that follows that pattern is finally not paying their loans. There's a few amount of people which still pays their loans. So we cannot be 100% confident of that prediction that we're giving, but we're fairly confident, and we say that the confidence here is 67.66. Here, let me tell you that this confidence is based on the Wilson score, and that means that it's not probability, it's not purely probability. It's not the number of instances, the number of customers that did not pay their loans over the total number of customers that followed that criteria. It's the confidence. It's something that also takes into account the total number of instances that follows this pattern. So a model is more confident if 90 out of 100 are backing up the prediction than if 9 over 10 are backing up the prediction. The higher the number of instances that follows the pattern, the higher the confidence that you can have in that prediction. That's what confidence gives us. And also, you can have another look at your data to find out which are the patterns or the groups that are really related to the fact of not paying the loan. You have a global view, which is the Sunburst view, and here you can see based on the different predictions. So if you predict 1, it's in orange. If you predict 0, so people that pay their loans, it's in blue. And you can detect here which are the conditions for the people that will not pay their loans. The way to understand this diagram is just thinking about the previous one, the one that looked like a tree with branches, but just as if you had a look at it from the top down. Imagine that you're looking at the top, and this is the root that you saw previously in the previous diagram. The root that contains all the instances. And from here, you start making questions, and your first question is, what's the number of times that this customer has been 90 days late? If it's 0, then you go into this segment of the circle. If it's 1, then you go into this other smaller segment of the circle. And so on. This segment is again split into, and if asking about the number of times late, if it's less or equal to 1, so equal to 1, it would be in that segment, new segment of the segment. And if it's greater than 1, then you would be in the zone where mostly the customers won't pay their loans, and that's why this sector it's colored in orange. That's the prediction that the model will give you for that pattern. So this gives you a global vision of where in the tree are the groups of people that you are interested in, right? Going back to the previous view, You can also have more information about which are the things that can be related to the fact of being seriously delinquent in 2 years. And the information that also can be obtained is, as I said, which are the properties in your data set that are more related to this fact, to the serious delinquency in 2 years. This is a histogram that is showing you the percentage of importance of each of the fields that you provided when trying to decide, when trying to predict and making these splits all throughout the tree. So you can see that the field that was more important for us to separate the data and classify it is the revolving utilization of unsecured lines. And this has a 23.29% of importance, meaning that all over the tree, the gain of information that this field has provided finally has represented this percentage over the rest of the fields. The second one in importance is the number of times that the people has been 90 days late, and it has a 16.28%. If you go on descending, you see that the least important of the fields that you provided is, for instance, the number of dependents, 1.42%. Why can that be important? As you know, each field, each information has a storage, retrieval, retraining cost. Finally, when you want to have information, you have to retrieve it, you have to keep it, you have to transform it. So these kind of fields that are really not found as significant ones in the model can save money in your business if you're trying to do it, or in your investigation if you're trying to predict some disease, for instance. Maybe you have to do some tests, and there could be very expensive tests, and when you build a model, if these results of these tests are not proven to be of relevance, maybe you can just skip them, and that would mean some savings in your business, right? So it's important to know also which are the properties that are really related to the thing that you want to predict according to your data. Now you've seen that we've extracted a lot of information, right, from the model. We've seen the patterns that led to the thing that we would like to predict. We've seen that there's the importance of the variables that you just provided, so which are the fields that are really important to be maintained. But finally, what we would like to do is, given a new customer asking for a loan, how can I label that customer so that I can take further action and decide what to do with that? That's the prediction. The prediction would label this new customer according to the data you provide from it, from it. And it can, thanks to that decision tree model, it can give you a confidence also of the model based on the data that it has seen, and also some explanations about which are the combination of rules. As you have a path, a significant rule, a pattern that led you to that prediction, you have that same pattern is telling you which are the fields that are determining, and their values that are determining that this loan is going to be in delinquency in 2 years, right? If you want to do that, of course, it's also easy. Let's come back to the actions menu here in the model screen and see that here you can see the predict action, and we'll be presented with a form where there's the mean values of each of the fields, but imagine that you are using unsecured lines of credit, and then you are more 90 days late. As you can see, there's here people that will be probably delinquent with a percentage of confidence, right? So here you can change directly the values for your new customer and obtain the label that will tell you what action to take according to that. Here you can change. Now we're seeing the results in the confidence results are being expressed in terms of probability. So the number of instances in our training data in favor of that prediction against the total number of instances, but you could also change the confidence or even select a positive class telling us what's the thing that I'm interested in and put a threshold. We'll see more about that. So in the next session that I'm conducting. So don't worry about that. But so far, but the idea is here that by putting the information that you have about the properties of the new customer, you obtain the label and the confidence that the model is giving for this label for you. So the next question is, well, my model is working, is telling me predictions, but can I really rely on that? Well, you might think, oh, if the model is very confident, well, I can be safe, right? Because it has seen many instances and then it's enough. Well, that's not correct. I mean, the model is telling you how sure it is according to the data it has seen and strictly to that. But your new customer will probably not be identical to any of the previous customers. And the model needs to generalize from the data of the examples that has been given. If the model generalizes well, the new customer will be given an accurate prediction. But if the model is, for instance, too greedy and wants to adapt a lot to the instances that you provide, it might be doing overfitting. And then when you give a new instance, the model will be wrong because it would not have been general enough. Or maybe he's doing the contrary, he's doing things too broadly, and then a new instance will not be fitted enough well. So we need another kind of method of ensuring that the model is doing good. And the thing that we can do to ensure that is evaluating. When you want to evaluate, you need to be sure that the instances that you will try and use to evaluate the model have never been seen by the model, because you want to evaluate the generalization of the model, whether if it's doing right generalizing, and the next customer that has never been seen in your model will also be correctly predicted. So what do we do to ensure that? A simple method can be just splitting the data that you have. If you have data enough, then you can decide to split the data in two parts. The biggest one, let's say 80%, will be the data that you will use for training, and the smallest one, let's say 20%, will be held out and kept for testing afterwards. You train a model with the biggest part of the data, the 80% of data, and then you use the 20% that you just kept apart, that the model has never seen, and make predictions with the model for that data. In this case, you will have the actual result of the serious delinquency, because you already had it in your examples in the holdout data, and also the predicted model, the predicted value that the model has given us. So you can compare whether the predicted value is equal or not to the real, to what really happened in that case, to whether the loan was delinquent or not. Then the evaluation, it's just aggregating this information, counting how many times we matched the real result and how many times we just missed this result. And that's what we are going to see in BigML right now. So let me go back to my original data set here, and let's do this workflow that I talked to you about. Let's split into an 80 and 20%. Here in BigML, we have a menu that lets you do that in a one-click too. I have here the configuration. As you see, it's 80, 20%. And let me add here a text. In this case, I will put BigML. It's just a seed for the random decisions that are just separating your rows into the training and test set. And this only ensures that every time I select at random, using this seed, the seed BigML, this text, then I will do it exactly the same way. I mean, I will do the same separation now and again if I use the same seed, even if the separation is just at random. I mean, I'm using the same random chain of numbers to separate that. And when I create this training and test, what BigML is doing is just picking at random some of the instances, creating one data set with 80% of the instances and another one with 20% of the instances. No instance in the training data will be part of the testing data. That's very important. Otherwise, the evaluation will be wrong, will be over-optimistic. And after that, I will be able to create a model from the training data and just evaluate, so make predictions with the test data, with the model for the test data, and see what results from it. And that will be the evaluation I was talking to you about. Here we have the 120,000 instances that have been selected randomly and put into the training data set. And I can create a model just as I did before for them. And then I will evaluate. Remember here, the graphics here, I will evaluate. So I will create predictions with the model to then aggregate the numbers of times that I match the results and the number of times that I don't match the results. So now I have a model. Again, going to the action menu, I see that there's an item and a link that lets you evaluate. And then if I want to evaluate, I see that the data set that will be used to test this model is the one that I already created in the split. BigML knows that you previously split your data set, so it automatically puts here the test data that was created. And we evaluate the model by creating predictions. Now, BigML is creating a prediction for each row in the test data set and is comparing the results of that prediction with the model to the real results. And here's the result of this comparison. Here you can see that there's a matrix that will tell you about how many times I failed and how many times I got right the result, the actual result, right? But finally, there's these aggregated numbers that we usually look at. And the first number that you usually look at is accuracy, right? I mean, people usually think, well, how many times did I match the result over the total number of times, the total number of rows of my test data set, right? The data that was provided to test. And here we can see that there's an excellent result, right? 93.8 of accuracy, and would be happy with it, maybe. I mean, if 93.8 times in percentage, we just nail the result, well, that's great, right? It's a great accuracy and everything goes right. Well, not really. So you probably in 10 seconds will be coming at me and say, hey, you sold me a dead parrot. And why is it that? Well, you need to imagine another experiment. You have a bag, and inside of the bag you have 10 balls. 9 of them are white and 1 of them is red. And you want a model that will tell you whether when you you want to predict when you will get out a red ball. And I will build a model for you that it's perfect and it's telling you you will always get a white ball. And this model is 90% accurate, right? Because 9 out of 10 times you will get a white ball. But this model is useless because what you're interested in is in the strange case where you get out a red ball. And then the accuracy in these cases where the minority class is very unbalanced and is the one that you are interested in is not a good measure of evaluation. So you need to think about other things like how many of the cases that I'm interested in do I get right? And that's what this diagram here reflects. So first you need to ask yourself, which is the class that interests me? And in this case, we're interested in the people that don't pay their loan. So we're interested in a positive class, which is when the serious delinquency in 2 years has a value of 1. That's what you see here at the top of the slide. And we can see here the results for the actual values that were in the test set and the predicted values that were predicted by the model, right? As you can see here, in the actual test set, there were 27,996 instances where people paid their loans, and 2,004 instances where people did not pay their loan, sorry. On the other side, when you predicted with the same data using the model, here we can see that we got 29,000 instances, 305 instances that were predicted to be paying their loans, and only 695 were correctly or incorrectly predicted to be not paying their loans. So the model is generalizing, but it's not nailing it totally. I mean, it's doing a job, and we need to be careful to analyze whether it has done a good job for our interests, for what we need to solve the problem, right? In this case, you see in a highlighted dark green these 422 cases that really were nailed. I mean, and these are cases where people did not pay their loans, had delinquency, serious delinquency in 2 years, and were predicted to do so. And these, light green, are the 27,723 cases where people did pay their loans and were predicted to do so. So these are the cases where the model really matches the real values that happen. But then there's this red and oranges colors that tell you which are the failing cases, the errors that we got with our predictions. There's 1,582 cases where the model predicted that people would not pay their loans, and where the people did not pay their loans, and the model predicted that they would pay their loans. And here there's 270 cases of the opposite case. I mean, where the people did pay their loans, but the model predicted that they would not pay their loans, right? So the important thing here is taking care of these different values. These are the true positives, so the class that we're interested in, the positive class that were matched by the model. These are the true negatives, the class that we're not so interested in, and the model also got right. And then you have the false negatives, so the ones that we thought that were negatives, but they weren't. And these are the false positives, so the ones that we thought that were not going to pay the loans, and they finally did. And this is the important thing when you analyze whether the model is doing right or wrong. Because remember the goal. When we stated the goal was predicting who will be 90 days past zero walls. And our idea is to minimize the cost of these loans that we're going to give. So if we want to minimize the cost, it has not the same cost not to give a loan to someone that was predicted that would not return, and if he would pay it. It's worse if you predict someone that will pay their loan and then he won't. So what's important, the important thing is maximizing the recall for the people that will not pay their loans, even if at the same time you are considering that more people will not pay them and finally they pay, right? Because it has a lower cost for the company, right? So our goal here will not be looking for the best accuracy, but looking for the best recall. How can we do that? Well, you know that we built a model, but we built a model by default. And models have some parameters that can be tuned. And we'll take advantage of that. We will go back to our training data set, and we'll build a new model from it. And now what we'll do is configuring this model. We will not build the model by default, but we will use all the different parameters. And in this case, we'll use a parameter that would help us minimize the imbalance that there's between the two kind of examples that we provided the model with, right? I mean, there's a huge amount of data telling us how is the people that pays their loans, but there's a few instances compared to that that tells us when the loans are not paid and there's a serious delinquency, right? And in order to compensate that, we can use these weights that you see here, when you select balance objective, what you're telling BigML to do is try to give a higher frequency to these rows that are describing the people that don't pay their loans to compensate for the difference of the number of instances that you have in your data against the people that pay their loans. So in fact, you're doing a frequency which is inversely the proportion of instances that are between the class that you're interested in, the minimal class, to the class of people that pays their loans, right? So you're trying to compensate for this imbalance, and each row of people that describes a loan that has not been paid will count more times to compensate for the rows that are describing the people that pay their loans. When I do that, I create a new model from it, and it's doing this process internally of weighting each of the rows that we know that are describing the patterns of loans that have not been paid, so that it gets compensated with the ones that have been paid. I get a new model, I create a new evaluation for it with the same test data set, of course, with the same data to be able to compare one and the other. And again, I do predictions with the new model until I find out the results, and I see that probably the recall, which is the thing that I wanted to increase, seems to be better. I can see here the comparison. Of course, what we've done is the percentage of the examples of the class that we were interested in was so low that we need to increase the frequency that in which we use it to for the model to learn from it. The model learns better, and what you can see is that in this case, the errors that were significant for us, which are these 1,582 that were predicted as paying their loans, and in reality they weren't paying, have been reduced, and also have been here. I mean, they were correctly predicted as people that will not pay their loans. At the same time, you see that this number has increased. I mean, the people that probably would end up paying their loans and have been predicted as people that will not pay their loans also has increased. But as I said, the cost of having these people here is lower than the cost of missing the people that would not pay their loans. So the balance model would work better. Well, the thing is that you see that there's different parameters that you can tune, not only this parameter that you see, the balance objective in the weights of the fields, and also there's different kinds of models. You've seen that there's different supervised models. There's the ensembles, which are collections of models, of decision tree models. There's the logistic regression. There's the neural networks. We could use that too. There's plenty of models. So what should I do? Should I try every parameter? Well, hopefully not. I mean, we can automate things. And in order to do that, we offer the OptiML. The OptiML is an automated procedure that is looking for you for the different models that we have, the different parameters that we can apply to these models in a smart way to find out which are these the combination of models and parameters that will get the best results for your data, because there's no better model than another. I mean, there's not a model that will work for any data better than any other model. There's the model that fits better your data, and that's what the automated procedure is doing for you. Is evaluating constantly different kinds of models in a guided way so that you can find out which is the one that will work better with your data. And to show you the results, because it takes some time, I've already built one for you. I built one for this data, and the results from it is, as you see here, that it has compared some deep neural networks and some different decision trees. And as to the recall, which is the thing that you have to ask for, the metric that you want to optimize, in this case is the recall, and the class 1, so the class of people, loans that were not paid, serious delinquency in 2 years equal to 1. Given these conditions, the model that has been proved to give the best results in this case, it's a simple 15-node prune decision tree. And you can see here the recall that it has reached, 85%, and you could even check the evaluation that it has. So remember that once your data is consistently uploaded to the platform and all the feature engineering, which we probably will hear in other sessions, is done, you can also use this automatic tuning procedure to smartly search for the best performing configuration, right? And finally, the winner can be a simple model, something that gives you a lot of information, it's easily trained, and you don't need the power, for instance, of deep neural networks, because sometimes these simple models will work better for you than the deep neural networks, especially when there's not lots of data to fit all the parameters that deep neural networks need. So this is where my session ends. Thank you for your attention. And if you have some questions, remember that we are on the channels. So see you in the next talk about predictions.